It's a pleasure today to have. So I guess your name is how do you pronounce it? Peter?
Yes.
Nandori?
Yes.
And he's from Yeshiva University, and this year a member at our institute here. And he will talk about hyperbolic billiards to statistical physics.
Yes, thank you, Camilo, and thank you for the opportunity to speak here. Just wanted to tell you that I have two screens, so it seems that I don't look at you, but actually I'm looking at you right now. I have the slides on the other screen. So yes, the title is From Hyperbolic Billiards to Statistical Physics, but as I was preparing the slides, I was thinking maybe I should have said it the other way around, from statistical physics to hyperbolic billiards. You'll see in a second why I mean that. So the plan is actually I'm going to give you quite a bit of history, maybe a little bit general motivations, discuss systems of hard balls, ergodicity, which is a big problem, and then go to Sinai billiards and discuss recent developments on Sinai billiard theory. And then last two sections are kind of a little bit moving from Sinai billiard back to the original motivation of systems of hard balls, which is non-equilibrium particle density and systems of hard balls with their interaction limit. And needless to say that you should ask any questions anytime you would like. So let me start with ergodicity, systems of hard balls. I didn't draw a picture here, but basically when I talk about systems of hard balls, I mean that you have, let's say, spheres on the two-dimensional box, and then they fly around freely. And once they hit one another, then they just collide and exchange energies, according to classical rule of mechanics. So this is very classical model. It dates back to Boltzmann, 1870s, and he formulated what is called the ergodic hypothesis. Actually, this is you can call Boltzmann the grandfather of ergodic theory. That he said that the time average should be equal to the spatial average in models of hard ball, in systems of hard balls. So this is very early reference, and of course it's a physics language, so he didn't exactly specify what limits you want to take, but this is a very important first idea. And then of course celebrated result by Sinai in '63. Well, first of all, ergodicity doesn't hold in a box, but ergodicity holds if you define particle hard balls on a torus. So in some sense you immediately quit physics, because in physics you can't have particles on a torus, but for mathematicians, of course, torus is a very natural place to look at. And he proved ergodicity of two hard balls on the two torus. And later, Boltzmann hypothesis was kind of more specified and renamed the Boltzmann-Sinai ergodic hypothesis, which states the same statement, ergodicity of hard ball systems, but any number of balls and any number of dimensions. Okay, so n balls and dimension d. And yes, go ahead, please.
I wanted to make sure I understood about this result about no ergodicity in a box. Does that mean if I have elastic bounces off the box and I put two balls in, it's not going to be ergodic?
Yeah, they might not be able to swap. Like if the radius is too big, they can't go around one another.
Oh, they're too big, but so are you telling me with a let's say reflecting boundaries, I don't have ergodicity ever?
No, I think if you have small balls, then you probably have. But if you have big balls, you...
Yeah, well, then I can understand. Yes. Mm-hmm. But that's the obstruction. The big balls will be the obstruction.
Yes, in fact, I'm going to comment quite a lot on whether you want to consider big balls or small balls, because some people consider big balls, other people consider small balls.
Yeah. Okay, good, thanks.
Mm-hmm.
Sorry, I had a question. By
yes.
ergodicity, you mean like up to like some measure zero set of initial data?
Yes, so ergodicity, well, Boltzmann said that the time average equals space average, right? But modern definition of ergodicity is that you have a measure preserving transformation, and the invariant measures all have either full invariant sets, either have full measure or measure zero. That's the definition of ergodicity. So here, well, it wasn't defined by Boltzmann, but in the language of Sinai, of course, it was already defined that you can consider the hardball system as, well, not a transformation, but let's say a flow. So it's a continuous time dynamical system. When you let you keep track of the motion of the particles, you fix the total energy, And then you have this nice phase space on which the flow acts. And ergodicity means that there is no invariant set which would have measure different from 0 or 1.
Right, thank you.
And so this was like a long battle, but finally Nandori proved in 13, as far as I understand, full-blown result, ergodicity for any D and any N. Now, I want to talk about Sinai billiards just in a second, for which results are available much beyond ergodicity. So if you are studying ergodic theory dynamical systems, then ergodicity is the first question that you ask, but there are several more questions that you can ask. Yes, go ahead. Sorry, I can't hear you very well. Can you speak up?
Can you hear me?
Yes.
In Simani's proof, is the radius of the balls matter, like in the previous case?
No, as long as you are on the radius of the balls. No, I think it doesn't matter. No. Okay. So, like one last sentence about ergodicity is Bunimovich's remark is that they were not very satisfied with working on the torus. So they considered another model, which is kind of more physical. So you have these red circles, which are fixed. The red ones don't move, okay? And then you have the blue ones, which move around. So it's no longer on the torus. I mean, it doesn't matter if it is on the torus because the blue cannot leave this cell. So it's kind of localized. So diameter of the blue one is bigger than the gap here, okay? But you have two blue ones, and they can, if they both come to the bottleneck, then they can collide with one another, so they can exchange energies. So this is a model of, let's say, 2, but they can do it for a finite chain. And then they proved ergodicity for this model. And this is a model that I want to come back to later, okay? So this is a little bit history about ergodicity. And now I want to go to Sinai billiard, for which we have.
Let me ask you a question.
Yes.
From your point of view, what's interesting to me is that you have very few particles and you have ergodicity. Are you interested in many particles or fewer particles, or is that going to become clear?
I think physicists are mostly interested in case of many
I know,
particles.
but from the point of view of dynamics, yeah, I'm just wondering what your viewpoint is.
Yes, exactly. This is a very good point, but very good question. But later, I hope it will become clear that if you only have one particle and everything else is fixed, let's say in this picture, you fix the red ones and you only have one blue, then you can prove a lot of beautiful results. So that's kind of a success story. And you actually, I'm going to review most of those results.
Okay.
Once you start to have two, then you have much fewer. Unfortunately, we have much fewer results, but eventually you want to consider like 10 to the 23, right? So,
okay.
Which is
so it is the many bodies that you're interested in. Okay.
Well, I'm interested in any question that I can solve along these lines, but eventually, yes, I would want to consider several particles, exactly.
So this is only for a chain, or you can do it, it can be done into some lattice of this sort?
I think they did it in the chain, but doing it in the lattice is probably not very much different. However, only 2 dimensions. Absolutely no way.
Yeah.
Higher dimension.
Okay.
Okay, so Sinai billiard, coming back to previous question, is the case when you have one particle and everything else is fixed. So I'm going to a little bit tell the story of that. So here is a picture. The gray, like first of all, this is on the 2 torus, and the gray things are fixed, and you have a point particle which is red, and then it flies freely and it bounces back from the boundary of these gray things, which I'm going to go scatterer. Okay, so billiard table is 2 torus, and you subtract these scatterers, okay, which are disjoint, strictly convex, and have smooth boundary. And now we can define billiard dynamics, which is free flight of point particle in omega and specular reflection on the boundary. So speed is conserved, so we assume it is just 1. And so we can define a phase space of this dynamics, which is omega cross unit circle, because the speed is fixed 1. So velocity is just on the unit circle. And this is phase space for the billiard flow. And people also consider the billiard map, which is Poincaré section. So can you hear me well? because my video is fading
Yes,
out
we
a
can.
little bit. Okay, sorry. Let me know if you can't hear me because my video is fading out. So anyways, the billiard map is kind of a technical tool that people use because discrete time is easier than continuous time and the map is easier to study than flow. So basically the map, so the map would take collision to collision. So from this point, you go to that point. So phase space of the map would be one parameter on the boundary of the scatterer and another parameter for the outgoing velocity. So the phase space of the flow is 3-dimensional, phase space of the map is 2-dimensional. And Lebesgue measure is invariant measure. So with these systems, usually there is a bunch of invariant measures, but physical measure is the Lebesgue measure. So I am basically I'm only going to talk about the Lebesgue measure, which is invariant under the flow and essentially invariant under the map if you define it correctly. Okay. So let me tell you history. We already discussed ergodicity, so this was proven by Sinai, and hyperbolicity as well. So what do I mean by hyperbolicity? I mean that stable, unstable manifold exist almost everywhere. Points on the stable manifold get exponentially close to each other in forward time, and likewise for unstable manifold in backward time. Now, so this is falls in the realm of hyperbolic dynamics, but there is some extra difficulty, which is due to the discontinuity. So if you have a grazing collision, then in a nearby the grazing collision, you may or may not hit the scatterer, which is going to cause discontinuities very clearly for the map. Also lack of differentiability for the flow. So for that reason, stable and unstable manifolds only exist locally and almost everywhere, which causes a lot of technical difficulties. And mixing was also proved by Sinai. So just I want to remind you of what mixing means. For example, I formulated it for the map, which is also true for the flow, that if you have, let's say, L2 test functions or measurable sets, then a measure of A intersection F to the minus NB converges to measure of A times measure of B as n goes to infinity. So it's sort of asymptotic independence, right? If you start from set A and you want to ask yourself how likely it is that you go to set B in a big number of steps, then eventually you kind of forget that you started from set A, right? It gets independent for n large. And next thing I wanted to tell you is central limit theorem, which goes back to Bunyamovich-Sinai. So for example, one way of formulating central limit theorem is that you denote by Sn position of the particle after n collisions in the infinite periodic extension, which is, in other words, you consider observable over the Sinai billiard, the compact phase space. And when you rescale by square root n, you will converge to normal distribution with non-degenerate covariance matrix. This is a most important version of the central limit theorem. However, of course, it is true in more generality, it's true for other observables on this dynamical system. But I think from the physics perspective, the most important question is if you have a particle and then you let it go in the billiard table, let's say infinite periodic billiard table, then after a big amount of time, where does it go? And it just goes exactly, it behaves asymptotically exactly the same way as a random walker, because it just satisfies central limit theorem. So position is going to be scaled by square root of time, and location is going to be given by Gaussian distribution. So this is actually, yes?
Is this all for finite horizon, or does that matter here?
Right, so it matters. So for simplicity today, I'm going to talk about finite horizon. In case of infinite horizon, there is a little difference. You need to put here a logarithm.
Yeah.
So, but other than that, it is quite similar. There is more technical issues, of course. So for simplicity, I only covered finite horizon here. And next milestone of the theory that I wanted to review is a result by Lai Sang. She proved the exponential decay of correlations for the billiard map, which means that it's a quantitative version of the speed of mixing, right? So we discussed speed of mixing before when I said that if you have test functions f and g, then the integral converges as n goes to infinity to the product of the two integrals. Now she's saying a quantitative control on the speed of convergence, which is exponential. So it's just, very fast. Of course, you need some regularity of the test function. It's not true for every test functions, right? But usual assumption is something like Hölder. I don't know, Hölder is a very natural class because it's, weak version of continuity in some sense. So this is important result. And I wanted to tell you the next result just because a little bit related to the topic that I want to talk about later is a kind of a technical version of the central limit theorem. So the central limit theorem, we discussed in details that in time n, let's say discrete time n, you go to a distance approximately square root n, but there is a very local version of that you pick a point at the distance square root n, and you ask what's the probability. Well, I'm just gonna use this terminology probability. I know it's not, but like what's the measure? Like I start with the invariant measure, and then I let the dynamics go deterministically, but I still use the terminology probability, just in the sense that you can think about it as initial condition being randomized, and then everything else is deterministic. So what's the probability that you travel to your favorite location, which is approximately square root n away from the origin, and that probability can be computed. Of course, it goes to 0, but it goes to 0 at the rate 1 over n. Well, 1 over n comes from the fact it's a two-dimensional thing. So the area of the disk of radius square root n is n. So if you pick a specific location of size big O 1, then the probability should be 1 over n, because the total probability over a domain of area n is 1. So that's not a surprise that it's 1 over n, and then the Gaussian density appears here. So this is kind of a technical result. Of course, is very similar to CRT, is a little stronger than that, but in my opinion is important because it kind of opens the door for further statistical properties. If you're a probabilist, then of course the central limit theorem is the first question that you ask, and there is a whole list of other questions. Maybe if you want to study heat equation, then central limit theorem is already what you want. But there are several points of view from which you can approach such models.
I'm a bit confused about something. So I mean, when you look at these Sinai billiards that you had earlier, and the way he explained it initially was, if you're in negative curvature, and this would be a limit of negative curvature where all the curvatures on the boundary, then if you have a surface of negative curvature, you have all these features. Then the central limit, I don't understand this periodic extension. That's something special to the torus, the two torus, the plane torus. The central limit theorem is still true, but that feature, what does it mean exactly? Dynamically. So if I'm compact phase space, right?
Well, I have a picture later. I don't know if I'm not sure if I understand the question, but here's a picture somewhere later. So this is what I mean by periodic extension. So you have an infinite. You cover your infinite plane with squares.
Yeah, but then it had to be a plane. I mean, so if I started with a surface of negative curvature, the universal cover is a hyperbolic plane, and then this feature is, I think, very different because of the exponential growth rate. So
yes,
on the other hand, the dynamics are very similar. You have positive entropy, you have mixing, you have
I agree. So in case when your fundamental domain can be, let's say you have a torus or you have a hexagon, which is basically a torus, you can unfold it in the plane.
I'm happy with that.
Then you have this very nice identification that you over the compact phase space, the hyperbolic dynamics, you have a test function, and that test function can be interpreted as the position of the particle on the plane. So it's just a selling point, right?
Right.
If you don't have this nice universal cover, let's say you have a surface of constant negative curvature, you can still consider test functions, and you can define the central limit theorem for those test functions, but they might not correspond to this kind of nice physical picture that a particle's position on the plane.
Okay, that was my point. On the other hand, the central limit theorem for a random variable along a path is still true in that setting.
Yeah, that's right. Yeah, that's right. But even here, you could consider other test function, right? The test function doesn't have to be the vector that is, here the test function would be the vector that is what you travel, like where, like this free path vector. If you consider other test function, that might not correspond to such a nice picture, but you still have the central limit theorem. It's a general statement for any Hölder function. So, okay. So,
one other question.
Yes,
for the Banimovic Stadium, all these things, I mean, I know most of it's true, but there you don't have uniform hyperbolic and you have still positive entropy and so on, and ergodicity. Are these other things true, like the exponential decay? I can't remember.
No, exponential decay is not true. In fact, there are several billiards for which people were able to show polynomial decay, even sharp polynomial decay. So there are several variations, Banimovic Stadium and billiards at corner points and Banimovic mushrooms and all these kind of things. But for simplicity, I only talk about the simplest finite horizon Sinai billiard, strictly convex scatterers, no corner points, no. Like, I mean, there is already a lot of technical issues here, so.
Okay.
For the Banimovic Stadium, its decay rate is 1/n. And if you just look at the particles that bounce back and forth between the two sides, that's 1/n, and that's as slow as it gets.
Yeah, I can see they're bad guys, but those are measure 0. Yeah. So I was hoping that typically you still have, no, okay, I understand.
Right, there are a lot of, yes, yeah, well, eventually I want to get to some, some results that, some of my results, and of course I could review everything, but then we run out of time very quickly. So I decided to focus on just the simplest case, finite horizon, the simplest Sinai billiard. Okay, so I wanted to tell you a little bit about this next milestone, in my opinion, next milestone, which is a standard pair technique. Is not really a result, it's more like a tool. I'm not going to go today very technical. So I'm just telling you there is such a thing as standard pair, which is basically you can think about standard pair as conditional probability. Let's say you prescribe something in the past. Let's say you wanted to travel along certain trajectory, a certain symbolic trajectory in the infinite extension. Then you know something about the past, right? The future is not independent from the past, but asymptotically gets independent. So you have some knowledge about the past, and that you can think about as some probability measure on a stable or an unstable curve. And then this technique, which was basically developed by Chernow and Dolgopiat, they work with this family of possible measures on unstable manifolds or something like that, the unstable curves, which is a smooth version of the unstable manifold. And with this kind of technique, pushing the idea of conditional probabilities into the realm of this billiard business, they were able to kind of prove much more results from your probability textbook, right? So if you open up your probability textbook, then central limit theorem is in the first chapter, but there are other versions. For example, almost sure invariance principle, law of iterated logarithm. These will also follow from their technique. So from the probabilistic point of view, this is kind of important, results. But you might argue that from physics point of view is not so much interesting, like law of iterated logarithm, whatever. So maybe a few more bullet points. That exponential decay of correlation we already discussed, but here I was talking about the map, and for the flow it was actually quite open for some time, but not so long ago it was proven by Balati, Demers, Liverani. So this point is just to tell you that going from the map to the flow is not so easy. Obviously, they both prescribe the same dynamics, but exponential decay of correlation for the map is a different statement from the exponential decay of correlation for the flow. And it turns out the second one for the flow is much harder to prove, and that's why it was only proven in 2018. And maybe I just put it in slightly bit smaller font size because this result is much less ambitious than the previous one, but we extended this exponential decay of correlation when we consider standard pairs instead of invariant measure, just because we always want to, let's say, if you want to do anything like beyond chapter 1 in your probability textbook, then you need standard pairs condition on past, and then you want to say that things decorrelate exponentially quickly with respect to the flow, even if you consider these more general class of measures. So this is a technical result which will be used in later when I discuss some more physical.
Peter, isn't the difference between starting from the standard pairs versus the invariant measure is that you don't have to start from an invariant measure. You can start from more general initial conditions. right?
Well, if you start from a measure which is absolutely continuous with respect to invariant measure with the smooth density, then it follows from Baladi-Demestre-Verandi, right? So here the novelty is that these measures are singular with respect to invariant measure.
They basically behave like the whole idea is that if you're on unstable manifolds, then it looks like it's almost the same as starting from the big measure,
I agree.
right?
It's almost the same. So in fact, as you can see, this is a smaller font size than this one because it's almost the same. But you know, strictly speaking, it's not the same, and sometimes you need it. And I also wanted to say that this local central limit theorem business, which we discussed before for map, we extended for flows. So you can do the same thing, like all these things that you want to do, exponential decay of correlation, central limit theorem, local central limit theorem, advanced statistical properties, you can now say for either map or flow, whichever you want. But for the flow, it's more recent, like these 3 references are recent. And for the map, it is usually at least 20 years old. All right, so maybe let's go back a little bit to physics. So remember that I discussed ergodicity, and then I moved to Sinai billiard. So next topic was Sinai billiard, and I discussed Sinai billiard in details. But what is interesting for a physicist? So here is this interesting paper by Bonetto, Lebowitz, and Ray-Ballet. So let me quote them. They say the following: the only Hamiltonian system for which a macroscopic transport law has been derived is the gas of non-interacting particles moving among a fixed array. Is a typo here. Is a fixed array. It's probably my typo, not theirs. A fixed array of periodic convex scatterers, periodic Lorentz gas, or Sinai billiard. Unfortunately, the absence of interaction between particles makes the system a poor model for heat conduction in realistic systems. To remedy the problem, it would be necessary to add interaction between the moving particles. For example, instead of points, make them little balls, and then derive coupled equations for the diffusion of both particle and energy densities. This is what we consider a satisfactory answer to the challenge in the title of this article. Of course, this problem is widely open, that if you have one particle, or if you have a bunch of non-interacting particles, that's the same question, right? Because you just decouple the particles and you study them one by one. But if you start to make them, let's say, instead of point particles, a little ball, and you start to interact with one another, the problem becomes much harder. I don't want to really, use big words here, but in my opinion, this is strongly connected to the 6th problem of Hilbert, which is of course vaguely formulated. So, other people can interpret the 6th problem differently, but I think Hilbert actually uses the terms that gas, particles, gas, and axiomatization as in probability theory. So that would be kind of a very, very important, a very important problem, but unfortunately widely open. If you could, let's say, study a system of small balls and derive what they say is actually, I think, very ambitious, to derive joint equation for particle and energy process, or conduction or heat conduction, as well as conduction of mass. Anyways, this is a big problem, and let's see what kind of results can we what kind of results we have that point in this direction. So one thing that I wanted to mention first is a result by Chernov Dolgopiat, who consider one heavy and one small particle on a Sinai billiard table. So let's like the same Sinai billiard table. Now you have 2 particles, but it's kind of just a perturbative result, because one particle is big and the other one is small. And then when the small hits the big one doesn't move much, just a tiny bit. So they take this limit when the big one is really big, and then they consider perturbation. It's a perturbative picture from just having one particle, and still it's kind of a tour de force work, and they can show convergence of the big convergence to certain stochastic differential equation by the trajectory of the big particle until the big particle hits the boundary. So it's kind of a very short in the macroscopic sense, a short time scale until the big particle hits the boundary. Now there is this totally different line of work that I really just want to mention very quickly, and I don't really want to go into it, which was initiated by Lanford and then completed by Bodino, Gallagher, and Saint-Raymond, in which they consider small particles, and they rescale. So they have a big number of particles which are small, but they consider short time scale, so short time scale that the particles don't recollide. So they collide with one another, but you don't wait enough until the same two particles collide again. And then they derive Boltzmann equation and eventually Brownian motion. So this is kind of very interesting, but I really don't want to go into it because there are other references in the Boltzmann grad limit. I don't want to review those. So it's one of the works that I think is important points in this direction, but they take a different limit. Again, going back to what Boltzmann didn't say what limit to take, so they took one limit, and this approach is taking a different limit so these two limits are different, right? Because here you have small particles and short time scale. Here you have big particles and long time scale. So these are different things. Okay, so now next thing I want to discuss is non-equilibrium particle density. Is a very modest goal because it is just again going back to the case when particles don't interact with one another, so it's kind of unsatisfactory. But let me try you anyways. Don't interact with one another, but there is something new, which is the non-equilibrium phenomena. So if they don't interact with one another, then of course energy cannot, energy is conserved. So non-equilibrium can only be implemented in the particle density profile. So when I say non-equilibrium, I mean non-equilibrium density. So non-equilibrium density of mass. So particle density. So the picture is this: you have a long tube, which I call the Lorentz tube, is a periodic configuration of Sinai billiards, and then you inject particles from both ends, okay, with different intensity, lambda left and lambda right, and actually, the end is also absorbing. So this guy was injected, came back, and then was absorbed right away. This guy was injected and went a little further. So most particles will be absorbed right away, but a few will make their way to the center of the tube. And again, this is
what is the intensity in this setting?
So intensity. Okay, so here it comes to be very precise. There is randomness coming from two sources. One of them is the time of injection, and this is given by a Poisson process. It's a random process, right? And the Poisson process comes with a parameter, and that parameter is lambda L on the left and lambda R on the right. This is two different constants. And then I also have to specify the initial condition, which can be a standard pair or invariant measure as you wish. And if you specify these two sources of randomness, then the dynamics is deterministic from that point on. So the randomness only comes from time and place of injection. And then what we have is, let's say you compute expected number of particles at the location x times L. So capital L is the length of the tube, which is gonna go to infinity, and time capital T. Okay. And then, as you would expect, there is limit. So one possibility is that you let time go to infinity, and then you let length go to infinity. Then this density is going to converge to linear function, which is just a harmonic function in 1D. It's just linear function, but it's not constant, right? So it's the non-equilibrium in the sense that the two endpoints are not the same of this linear function, and maybe slightly bit more interesting limit, which is sometimes called hydrodynamic limit, when you let time and space go to infinity at the same time, right? So space is L, then time needs to be L squared. So it's T times L squared. Then you're gonna get a limit, which limit is just solution of heat equation with boundary conditions given by injection on the two ends. So this is non-equilibrium density profiles in Lorentz tube, which is a joint work with Dima Dolgopiat. And maybe one remark is, of course, 2 dimensions, right? Well, we can't go beyond 2 dimensions, at least. I didn't say that, but the Sinai billiard story is in infancy in higher dimensions. So all these, like 99% of the results that I said are only available in 2 dimensions. So here we consider this 2-dimensional domain with a student, Trevor Theolis. And what we prove is very similar results. So I didn't spell out in details, but maybe I tell you the limitations of the results. So there is 2 setups, okay? First one is that we consider any domain in R2, which is, piecewise smooth boundary, no cusps. But other than that is, any domain on which you want to consider heat equation, let's say. And then you do the same business as before, that you scale you pick larger and larger version of this domain. So you have larger and larger, like let's say you scale it by L goes to infinity, and then you inject on the boundary, and this injection needs to be induced by the invariant measure. So it's a very specific ways of injecting. So you inject in a way as if you just had the invariant measure on the boundary, which is kind of a fake one, but you can do it. And then you get the same results as in the previous slide. You have convergence to heat equation and the non-equilibrium steady state as well. So in fact, the proof of this result is very simple, because if you revert billiard dynamics, you should consider billiard in negative time, that's also billiard, right? So instead of going from the boundary and asking what's the probability that you get to a certain location in the center, you can revert the time and say you start from the center, and the question is where do you hit the boundary? And that kind of question is well known to follow from, well, not the central limit theorem, but from convergence to Brownian motion, which is known from, well, not Bunyamovich-Sinai, but morally speaking, it's known for at least 20 years. So this first statement is easy to prove. And we have a second statement when we want to consider more general injection, not just invariant measure, but according to standard pairs. Well, the eventual goal of this approach is that consider some natural heat bath on the boundary. And if you consider any reasonable heat bath, it's not likely to preserve the invariant measure of the bulk dynamics, right? Why would it preserve the invariant measure of the bulk dynamics? So it's really kind of fake to induce, to only consider invariant measure for the injection. So in the second statement, we consider any injection mechanism. You have an intensity function on the boundary. It's not just 2 points. It's not just left and right, but it's a continuous function defined on the boundary of this domain. But then, unfortunately, you can only prove for rectangle. So this is what it is. But anyways, this is.
Is that such a serious? I mean, I think most people would be happy to do it on a rectangle, so I don't see why that's such a terrible thing.
Oh, you don't. Okay, that's good. I like that it's at least we have it on the rectangle, but on the other hand, the first statement is any domain. So it is.
Well, yeah, okay, but yeah, it's rectangles. Certainly.
Well, rectangles have this nice product structure. So basically, it's kind of if you inject this guy, then the only way this guy can be absorbed is because of the first coordinate, unless you are very close to the corner. But you discard small neighborhood of the corner. And then it kind of this absorption mechanism is kind of can be reduced to the one-dimensional case if you are on the rectangle, morally speaking.
So, but I didn't understand this absorption condition, because I didn't. You said it, but I didn't understand how it enters your. I mean, the absorption is very important, I suppose. I mean, you have to have it, otherwise you're not going to have a.
Yeah, well, what we do is that you inject, and then if you come back to this, if you come back to the side,
yes,
then you kill the particle.
Yes.
That's just it. That's the only.
That's all. But and there's nothing else you have to say.
No.
Okay. So if I come back at all, I mean, what if I came back after 2 collisions? That would be.
Yeah, you can come back after whatever number of collisions.
And
anytime you come back.
If it does come back, you just kill it.
Yes. Well, in physics, people consider heat baths. Sometimes they say if you come back, then you get some random boost or something. Well, we just say we kill it because, that's one way of doing it. We have the constant intensity of injecting, right? So if you didn't kill it, then you would have to scale differently because.
Yeah, no, you have to do something. Otherwise, just build up particles.
Yes. Otherwise, the number of particles will just grow to infinity.
Yeah,
right?
yeah. But okay. But why isn't this very much like a Fourier law or what? I mean, how is this different from proving a Fourier law?
Well, you can say the Fourier law, but this is only for particle density, right? So we don't have a natural way of talking about energy because there is no energy exchange. I mean, you could say that particles have different energies, right? You could say that you inject particles at different energies, but it's kind of fake because they will not exchange energies with one another. So I don't think there is like, but it would be cheating. So
the particles that you're injecting, they will interact with each other, right?
No, they don't interact with each other. It's just point particles. So it's
they only interact with the boundary. Okay, yeah.
Yes, yes.
Okay.
So it's kind of a step back because they are only.
Okay, thanks. No.
Now, I still have time. Good. So I want to discuss the case when particles start to interact with one another. Okay. So there is this concept of rare interaction, which I'm kind of a strong believer of. And the idea is that if you have multiple interactions with between the same particles, then the problem usually becomes very difficult. Usually it kind of leads you to a higher dimensional billiard, right? For example, if you have a hardball system, then you can represent hardball system as a high dimensional billiard. And high dimensional billiards are difficult to study for multiple reasons. Not the central limit theorem is not known for high dimensional billiards. There is some conditional results conditioned upon some property of the discontinuity set, which is unknown to hold. So there is like a conditional statement. But again, okay, maybe I shouldn't really go into the high dimensional problem. Let me just say this, that in high dimensions, what is known is that if you have strictly convex scatterers, then under certain condition, the central limit theorem holds. But this condition is not known to, we don't know how to prove that condition. And furthermore, if you have hardball systems, they unfortunately lead you to a high dimensional case, which is not strictly convex scatterers. So for that case, basically no result is known besides the ergodicity, right? Ergodicity I discussed on the first page. That's a great result, but we don't really have any progress in the direction of central limit theorem or anything like that. So that's why I believe in the rare interaction case. Then you tune certain parameters in a way that you make interactions less and less frequent, and between any interactions, you approximate by some nice dynamics. So this is the first kind of step in this direction. That let's consider two particles which have small radius. So as just in the paper by Bonetto, Levovitz, and Rebelli, you replace point particles by small particles, right? So you consider two billiard balls with radius epsilon. And let's say one of them has speed 1 and the other one has speed lambda, where lambda is between 0 and 1. Just let's say rescale time in a way that the faster one has speed 1. And then what we prove is the first time they, so what do you expect? What is going to happen? So if epsilon is eventually going to go to 0, so what you want to see is that, well, sometimes they meet and exchange energies, right? But in between two meetings, they kind of move around independently from one another. If they were totally independent from one another, then there would be like a memoryless property, right? So the time that they meet should have exponential distribution, like in the case of Markov processes, right? If you have a pure jump Markov process, then the time in between any two jumps is exponentially distributed random variable because it's memoryless, right? The only way it can be is memoryless because it can't have a memory, right? The particles don't remember when they met the last time because they mix well independently from one another on the phase space. So you expect it to have exponential distribution of the time of the meeting. And this is exactly what we proved here, that there is a technicality that it works for almost every lambda. So that's what it is. For almost every lambda and for any fixed time capital T, when you let epsilon go to 0, then you ask what's the probability. Again, probability just means starting measure is invariant on the billiard phase space. Now it's a product of two measures, right? Because you have two particles. So with respect to this measure, the probability that they collide before flow time T over epsilon is going to be given by the formula as the exponential distribution, and you can compute this function rho of lambda. Well, it obviously depends on lambda, right? Lambda is kind of the speed, but it's a relatively nice function. It doesn't go to 0 as lambda goes to 0, right? Or lambda goes to 1. Why would it? So if lambda is equal to 0, then you actually just get here. Well, this 2 pi cancels, so you get 1 over omega. So if lambda is equal to 0, that means one particle stops. And if one particle stops, then the other one can still hit it, right? That case, I believe, must have, that case was known before because some people study these kind of questions of systems with holes. You have a dynamical system, and then you pick a point, and whenever you hit small neighborhood of that point, then you stop the process. So you got a hole in the phase space when everything leaks out. The question is, when do you hit it? And if you don't hit it, then how does the measure look like? Stuff like that. So for lambda equals 0 is known, but we proved it for lambda, or almost every lambda in between 0 and 1. But we didn't go beyond the first collision. So it's like, you know, baby steps. Most of the time is just the first collision. Of course, one expects to see Markov process of energies as you go beyond the first collision, but we didn't prove it. There are several issues with these two particles. So let's say, how can you simplify the problem if you have two particles? Well, you could consider a particle and a half, right? So the next thing, okay, sorry, before going particle and a half, I wanted to just tell you this basically along the lines of the proposal of Gasper and Gilbert. So Gasper and Gilbert in 2008 is two physicists. So this is a physics paper. They don't prove things, but they came up with a reasonable proposal. So they refer back to the Bunimovich, Liverani, Pellegrino to Suhov model, which I showed you on the very first page. Probably it was, you know, some time ago, but these were the localized disks. So these were they were confined in the cell. They couldn't go out of the cell, but they could stick their nose to these bottlenecks so as they could exchange energy. So they consider this model. They go back to that model, but they consider parameters in a way that the interaction rate goes to 0, and that's again a rare interaction. And they suggest that, you know, one should show that the energies converge and at a mesoscopic timescale to a pure jump Markov process. They actually compute the transition kernel of the pure jump Markov process. You can make such computations, but they don't. You don't prove, but you know you can make such computations. This would be step 1 as a master equation or a mesoscopic step. And step 2 is you have a Markov process. You can define this Markov process for a long chain, right? And then you let the length of the chain go to infinity, and you only work with Markov processes. And then you want to see if you let the chain length go to infinity, then these Markov processes would converge in the limit to solution of some version of the heat equation. But this step 2 is a whole different story. It doesn't do anything with dynamics. You start with Markov processes a priori. It's a problem in probability theory, so to say, and then you derive some thermodynamic limit for a Markov processes. So it turns out, in fact, step 2 is also highly non-trivial. So the model that they proposed, step 2 is not available because it's there is this whole industry. People study interacting particle systems, scaling limit of stochastic interacting particle systems. There's a condition which is called the gradient condition, and the Markov process that they get in step 1 is non-gradient. And for non-gradient, you have much fewer tools available. It turns out they can't do it. However, let me go back to this idea of a particle and a half. Okay, the particle and a half is another proposal. So I actually have a video. Let me show you the video. This is the video. Actually, it was done by Thomas Gilbert. This video. Well, it's kind of a two-dimensional arrangement, but you really want to think about a one-dimensional arrangement. So you have instead of two particles, you have a particle and a line segment, which you call a piston. And you know, the advantage of the piston is that it only moves along a one-dimensional line instead of the two-dimensional plane. So you, instead of 2 degrees of freedom, you have 1 degree of freedom. So it's a particle and a half. And then they exchange energies when they go into this bottleneck. And then you here in this picture is very clear that this would be epsilon, and then you let epsilon go to 0. So you consider smaller and smaller chance of interaction, and then you rescale time, and then you want to show convergence to Markov process. So this was next proposal for particle and a half. And I just wanted to tell you that this is a problem. Okay, so yeah, here is just the formula for the transition kernel. It's not very important. This formula is now, you know, meaningless. Just saying that you can compute this formula is actually not so bad, right? So it's an explicit formula, and what we do now, and this is I hope to be able to finish it while at IAS. So this is one of the things that I'm working on right now, is the rigorous version of this. So actually, there is one more thing. So in the video that I showed you, if you model it as a billiard particle and the piston, then the billiard particle, as you can see, is moving around in this diamond shape region. And one issue with the diamond shape region is that it has this point, which is called a corner point. So the boundary is not not smooth, but only piecewise smooth. And there is a lot of issues with the corner point. Well, in the second section when I was talking about Sinai billiard, I didn't talk about corner points because there is fewer results available for corner points. So we get rid of the corner point by this construction, that you do the business on a square. Well, the square has a corner, obviously, right? So it does have a corner, but the point is that you can unfold the square. So we do unfold the square. So this is what happens when you unfold the square, right? So you have a billiard particle on the square. Well, not subject to these scatterers as usual. So these, I should have denoted them by gray. Sorry, I don't know why I didn't put them gray. So these are what used to be gray scatterers. You can't go in the scatterer, right? So this is a Sinai billiard, and then you have this red piston, which is moving back and forth along this blue line interval in a way that the blue line interval intersects in this small range with the square of size epsilon. Then you let epsilon go to 0. And actually you need to rescale time by epsilon squared. In the previous model, you needed to rescale by epsilon, but here you need to rescale by epsilon squared, just because the area of this small triangle here is epsilon squared. So chances that you hit it is just scales with epsilon squared. Anyways, what you can do here is that you can unfold it, right? So billiard in this square subject to the scatterers is the same thing as you unfold is going to be billiard on the torus when you unfold the scatterers. And then this small triangle, which is this region of interaction, unfolds into a small square. And that square, you can think about this square as a moving square. Most of the time is not there, right? Because whenever the piston is here, you know, time 1 minus epsilon, the piston stands in this region. So this square here is non-existent. But whenever the piston comes in, then you have this small square that appears, grows up to the size of epsilon, and then it disappears again. So you have a Sinai billiard particle which moves around here most of the time freely, except for occasional times when this blue square appears. So the advantage is when the square is not there, then this is a finite horizon Sinai billiard without corner points. And furthermore, the blue square is bounded away from the boundary of the scatterer, so you don't have this issue of colliding with the piston as well as colliding with the boundary at the same time. So that would be another technical issue. So I just wanted to show you this picture in 3D. So this problem reduces to a 3-dimensional billiard, whereas the Gaspar-Gilbert would reduce to a 4-dimensional billiard, right? Because you have two particles. You know, position of each is 2 dimensions. So you can represent them as a 4-dimensional billiard. This one is a 3-dimensional billiard because it's a particle and a half, a particle and a piston. And in the 3-dimensional billiard configuration space would look like this. You have these cylinders which would correspond to these. Actually, I would have to draw, you know, much more cylinders, but then you won't be able to see the picture. So as many cylinders, as many scatterers you have on this picture. I only drew 2. And then there is this extra guy, which is the square that it grows in time, that corresponds to this kind of diamond shape. So it's a polyhedron, which is just size epsilon, and then you have this billiard. It actually corresponds to a billiard in a 3-dimensional domain. But the 3-dimensional domain would look like almost 2-dimensional times just the vertical line, except for this small guy, which is size epsilon. And then we can just say that each time you hit this guy, then you have to wait a lot of time before coming back, right? But you have to quantify it And the way you quantify it is that you approximate the thing with the two-dimensional billiard, right? Rare interaction. You approximate thing with a two-dimensional billiard, but on the technical level, what you have to little bit worry about is that when you approximate with the two-dimensional billiard, then when you actually have this interaction, then you may turn unstable directions into stable directions, and that would be disaster, because that would mean that you have like when I say approximation, I say like pretend that they move independently. Okay, there is an unstable direction defined for that, and when they actually exchange energies, then there might be a disastrous situation. Then this unstable perturbation turns into stable perturbation, and then your approximation totally breaks down because you are on the stable manifold. Or maybe not on the stable manifold, but arbitrarily close to stable manifold, and then you cannot approximate. So actually, this is the main point why here we couldn't go beyond. So in this model, where is this picture? Sorry, this picture. This actually happens in a pretty ugly way. That once the two particles collide, then it is possible that unstable direction of one particle multiplied by unstable direction of the other particle. So it's like an unstable plane that turns into the stable cone. So that is an issue which doesn't exist here. Just because you can, it's a simple geometric argument that unstable perturbation can only turn into stable perturbation if something like the piston stops, and that you can rule out by a small measure argument. So that's basically what is the advantage of the particle and the half. And then we have this, that energies converge to pure jump Markov processes times 3 scaled by epsilon to the -2. You can of course explicitly spell out the Markov transition kernel, which I didn't because it's just an ugly formula, but you have this explicit. So there is, yeah, this result is in progress, but I think the major obstacle of this unstable perturbation turning into stable perturbation is overcome. So that's what was the big issue in the other model. So I'm kind of optimistic about this being finished soon, and that's pretty much end of my talk. I put here some references, but that's kind of stupid because you cannot click on the link, right? So yes, that's all what I wanted to say. So
thank you.
Please.
Questions?
You were mentioning the fact that I forget, it was Gilbert and somebody who had this model, but then you couldn't calculate, Gaspar and Gilbert, right?
Right.
But then the problem was that your Markov process was you have an interacting particle system, but there's not a gradient type. That
correct? Yes.
But is there any hope of doing something with that?
So as far as I understand, there is hope. There is a group of people, especially Makiko Sasada, who is working on these things. And as far as I understand, she says that the case when you have piston and particle should be doable.
Mm-hmm.
But I don't think she did it, and I don't know exactly what is the state of the art. But she was optimistic, at least for the. I think she was also working with Herbert Spohn, but
yeah,
maybe not on this. Maybe not on this problem. So
okay. Yeah. So are you thinking about other even longer time scales, epsilon -3 or something, or is that gets to be too much?
Well, it's not yet.
But the epsilon to the -2 looks like it's in good shape. That's what you're telling us, right?
Yes, it is in good shape. So the Gaspar-Gilbert approach has limitations, right? You might argue that this model is not physical at all, right? What does that mean that this, line segment is moving back and forth? And why are you allowed to separate the timescales, right? All these are legitimate concerns.
Mm-hmm. I see.
But still, I think it is nice to turn some physics intuition into a mathematical proof, even if it is.
Have you looked at the work of Markov and Strombergson?
Yes. Markov. Yeah, so I said that I don't really want to, go into this.
They have a nice use of Ratner there. Yeah.
Yes,
quite use of homogeneous dynamics in their work, but it's quite okay.
So,
I mean,
so what they do is, so it's quite different limit. So what they do is a different limit, and they like you have the original paper by Markov Strömbergsson, and in fact they have some follow-up work Markov and Balin taught when they so they take this Boltzmann-Grad limit and then they let time go to infinity, and then they prove convergence to Brownian motion. But it's still from that it's still the same limit. So you cannot bridge between the two limits in some sense. It's widely open. And in fact, there is a nice related problem that I work on with a student, that we consider a high dimensional billiard with infinite horizon. And we just ask the geometry of the long flights. So you have spheres of radius less than a half. Then you have a very long flight. And then when you hit a scatterer, then you're gonna have another long flight. And when you hit the scatterer, you actually have, let's say you have this d-dimensional, let's say you have these d-1 dimensional hyperplanes. And when you hit the scatterer, you are basically among small scatterers, because close to the point where they maybe it's a little bit difficult to explain, it's like with my hands, but so let's say you have 3 dimensions and you have a 2-dimensional plane which is tangent to the spheres, right? Now you lift this 2-dimensional plane a little bit, then the intersection of the spheres with this 2-dimensional plane is going to be teeny tiny circles, right? And particle is just flying among these. So you are back in the Boltzmann-Grad regime. And then we try to apply with the student Markov Strömbergsson result to say when is the first time when you actually hit a scatterer, and then you go out of this corridor. So that's kind of another way of bridging between the fixed scatterer size and the small scatterer size. But that's again is just a small footnote, because this argument is just one end of the spectrum. When you have fixed radii, then you ask how long do you fly, but that's sometimes you don't fly long, right? And then the approximation of course breaks down.
Yeah, what I like in that work is it actually used eventually some quite non-trivial work of Marina Ratner.
Yeah, sure. It's a beautiful work. It's very, very remarkable. Yes. Yes, very nice. They even do more stuff, like they do quasi crystals and stuff like that these days.
Yeah, okay, but you certainly answered my first question, whether it's many balls, big balls, small balls. You spoke about every aspect of it.
Yes.
Great talk, yeah.
Do you ever think about quantum analogs of these systems?
Well, I did not, so I don't want to comment on those. Well, okay. I'm not knowledgeable enough.
Any more questions? Oops, the video disappeared.
Oh no, I stopped sharing. But if there is more question, I am happy to. I'm happy to share again. If
no,
someone
just joking. That does not seem to be the case. Then thank you very much for the beautiful talk.